Good morning, friends. So, today I'm going to discuss about another fantastic chromatography, that is ion exchange chromatography. There are very many chromatographies existing in the scientific world, like gel filtration, HPLC, high performance thin layer chromatography, HPTLC, paper chromatography, affinity chromatography, hydrophobic interaction chromatography, HIC. So many varieties of chromatography techniques are existing. So what type of molecule you want to purify, what type of molecule you want to separate. First, you should have a background idea whether if you know the molecular weight or if you know the molecular size, if you know the polarity index. So if you know at least a few parameters about your molecule of interest, then it will be easy for you to select the appropriate chromatography. So before selecting the chromatography, crudely you should not select. You should have some idea about the properties of the molecule which you are going to separate. So I'm going to introduce the chromatography, ion exchange chromatography. Then I will be discussing about different types of stationary phase material, that is resins, then principle of this chromatography, then how to proceed with this, and finally I'll end up with applications. So, ion exchange chromatography was proposed by three eminent scientists. One is Small, Stevens, and Bowman. You can see this gentleman is Bowman, and the middle fellow is Small, and the extreme right gentleman is Stevens. These three eminent scientists, they invented this particular technique, that is ion exchange chromatography. uh, Exclusively, this chromatography play a major role for the separation of charged species. So this is an outgrowth of ionics chromatography is an outgrowth where ion exchange chromatography, again it is a type of absorption chromatography coupled with the additional characteristic features of desorption. The primary uh, goal or primary principle of this particular technique is absorption followed by desorption. So adsorption, desorption phenomena was associated with the ion exchange chromatography. So here you can see this is a stationary phase material. The stationary phase material or a resin is divided into two portions. One, you can see this red color balls plus red color balls. So this is the functional group of resin, right? That is a positive charge is the functional group of the resin. This is the fixed part of your resin. And there is another blue color balls, you can see negative charge. They are interacting very weak through non-covalently. It's nothing but ionic interaction. So they are interacting through electrostatic mode with the functional group of your resin. So this blue color balls were actually termed as counter ions or diffusible ions or mobile ions. All three names are synonym: counter ion or diffusible ion or mobile ions. So this plus is fixed, it is immobile, they are not moving, they are part of the structure of the resin. Whereas this small negative balls, these are the counter ions interacting very weakly with the resin. They can be exchanged. You can see a sample is coming inside, the sample is having a negative charge. So the negative charge ion, negative charge blue color ball was removed. Instead, your sample, negatively charged sample, is interacting with the positive charge resin. This is how the separation or purification is happening. That's why the name of the technique is termed as ion exchange. So your your ion of interest is negative charge, it is anion. Now this is an example for anion exchange resin. Anion exchange resin will have anions as counter ions. So when negative charge sample molecules enter, this there will be a competition between already available negative charge ions with the sample ions. So this negative charge ions will be removed and the sample negative charge anions will interact with the resin. So in this way you are able to separate or purify. Here the positive charge molecules or neutral molecules cannot interact, they will move as such in the column. Only negative charge ions can separate it. Similarly, if the stationary phase material is totally opposite, assume this is negative, this red color is negative and blue color is positive, that is cation exchange resin. So here positively charged cations in the sample can be easily separated. They will be separated very effectively. Negative charge molecules and neutral molecules will not get separated, they will move away. So this is the outline principle. So as I said earlier, there are two type of resin. One is cation exchanger resin, another one is anion exchanger resin. So in the case of cation exchanger resin, you can see this is cation exchanger resin. So this cation exchange resin will have this is anion exchange resin. This anion exchange resin will have positively charged molecules as an integral part. Now you can see this is the fixed. This is anion exchanger resin. It is having a fixed positive charge. So now this is the fixed positive charge. To this, the counter ions or diffusible ions or the mobile ions, they are negative, they are anions, they are interacting electrostatically with the positive charge of your resin, which is the functional group of the resin. So what happens when sample molecules enter? Positive charge molecules will move away as such, neutral molecules will move as such inside the column, whereas the negatively charged anions will compete with this already existing anions and it will exchange. So this anion will get exchanged with the sample anions. Similarly, when you go for cation exchanger resin, the fixed, it will have a fixed negative charge as the functional group. You can see this is the cation exchanger resin. It will be having the fixed negative charge, that is the functional group of the cation exchanger. The mobile ion or counter ion or the diffusible ion will be positively charged cations. So when you add a mixture of analytes which contain positive, negative and neutral molecules, the negatively charged molecules will move as such through the column without any interaction. The neutral molecules once again move through the column without any interaction, whereas the positively charged molecules will create a competition with already existing this positively charged cations, and this positively charged cations will be removed. Instead, the sample cations which is present in the sample, they will interact with this exchanger. So in that way you can effectively purify or separate cationic molecules. So if you use anion exchanger, you can effectively separate or effectively purify anion macromolecules or anion molecules. If you use cation exchanger, you can effectively separate or purify cations. So weight doesn't matter. So here the separation or purification is not happening due to the weight. Whether the molecule could be a very low molecular weight or it could be a higher molecular weight, weight doesn't matter. Weight is not an influencing factor, only the charge. So here the weight of the sample cations may be 10 kilodalton or 20 kilodalton, or it may be just 15 dalton. So weight doesn't matter. Positively charged cations will get purified, will get separated if you use cation exchanger. Negatively charged anions will get separated if you use if you use anion exchanger. Now here you can see this is this is the functional what to say, this is the OH is the diffusible ions, right, highly distributed. Here you can see. So what could be the which group or which part of the resin is responsible for the fixed integral part for contributing the negative charge in cation exchange resin? It could be a sulfonic group or a carboxylic group, or it could be a phenolic group. So these groups are responsible for the exposure of the fixed negative charge or immobile negative charge. This is the integral part of the resin, or it could be acting as the functional group of the resin. So please remember, for cation exchange resin, the functional group will be negative charge. For anion exchange resin, the functional group will be positive charge. So this you have to remember. So if negative charge is the integral portion, then the diffusible ion or counter ion will be opposite. That means it could be positive charge. So equal amount of positive charge cations could be balanced. So the positive charge may be Na plus or K plus or Ca2 plus or H plus, even simple proton can act as counter ions in cation exchange resin. In anion exchange resin, the counter ions or diffusible ion or your mobile ions will be negative charge. So here chloride or sulfate or hydroxyl group can act as the diffusible ions. So it could be the exchangeable ions. So here you can see you can use different types of resins. So the name of the stationary phase material which we are using in ion exchange chromatography, usually it will be termed as a resin generally. So it could be a sephadex or sepharose or cellulose or polyacrylate or polystyrene. The most popular exchanger will be polystyrene based. So here you can see the trade name is amberlite. For poly, if you observe a polystyrene matrix, the trade name is actually amberlite IR 120 or amberlite IR 45, or you can see duolite, either amberlite or duolite. So the most popular resins will be of amberlite or it will be of duolite. So here you can see amberjet 1600H. It is a strong cation exchange resin where the functional group will be sulfonic acid and the diffusible ion will be proton. Whereas there is another resin PPC 100H. It is also a strong cation exchanger. Here the functional group again it is same, whereas the diffusible ion or exchangeable ion will be Na plus. Whereas for anion exchanger you can see purolite A500. It's a very strong base anion. So here the functional group is quaternary ammonium salt. So that is the functional group. Whereas the diffusible ion or counter ion is Cl minus. So for cation exchanger, the diffusible ion will be cation. For anion exchanger, the diffusible ion will be anion. For cation exchanger, the functional group will be negatively charged, whereas for anion exchanger, the functional group will be positively charged. So this finest difference you have to understand. So that is the name. You are going to purify a cation. If you want to purify a cation, then you have to use exchangeable cation, that is cation exchange. If you want to purify a separate anion, then you have to put an anion exchange, that is anion exchange resin. So you can use say for example different type of cations like proton, sodium, potassium, ammonium, rubidium, cesium, silver, lithium. You can use different, even you can use bivalent cations like Ca2 plus or Pb2 plus or Mg2 plus, Zn2 plus or what to say Cu2 plus. So you can use even bivalent ions, or even you can use monovalent ions as cations. For anions, you can see different varieties. You can use sulfate, you can use iodide, you can see bromide, you can use nitrite, you can use chloride, you can use bicarbonate. So different type of diffusible anions are also available. You can use. So I have already explained the principle, right? So if you use anion exchange resin, anions will be exchanged. It will be stuck up with the column. Cations and neutral charged molecules will move or washed away in the column as such. Whereas in cation exchange, cations will get exchanged. Cations will stuck up in the column. Anions and neutrally charged molecules will get separated. So the principle is very simple. Here exchange property, that is the backbone principle. Your exchange, if your interest, if your molecule of separation interest is positively charged, if it is a cation, then use cation exchanger. If your molecule of interest is anion, then use anion exchange resin. So here exchange is happening. As a result, you are separating or purifying the molecules. So you take a glass column, the instrumentation part, you take a glass column which is having a length of about 25 to 40 centimeter. So the diameter could be 1.5 centimeter. You decide the column size. This is for manual. If you go for a HPLC, then the column size will be very short and the diameter will be too short. So that is the reason why we are giving pressure in HPLC in order to prevent the back crack of the column. So this is a very simple manual, not a sophisticated automated column. You can go for even a manual based ion exchange chromatography. Uh, Take a column with a minimal size of 25 and you can increase the column length up to 40 or 50 centimeter. You can fix the diameter to 1.5. Then you can increase the bottom of the column using absorbent cotton, or you can use a glass wool. Glass wool would be the most appropriate choice, so you will get a free flow of the mobile phase. You can plug the bottom of the column using a glass wool, and then you can introduce the exchanger. So you decide whether if you want to separate, you want to purify anions, then use anion exchange resin. If you want to purify or separate the cation, use cation exchange resin. So you select appropriate exchanger resin, then you fill the exchange resin up to a height of 10 or 15 centimeter. If you have selected 40, then you can go up to 15 to 20 centimeter height for the filling of the resin. If you have if the length of the column is 25, then you can reduce to 10 centimeter height, right? If it is 25, then you can move up to 8 to 10 centimeter height of the packing of stationary phase resin. If you have selected a column with the length of 40 or 50 centimeter, you can elevate the stationary phase material bed size from 50 to 20 centimeter. So you decide the height of the column material, packing of column material according to the size of the column. So this is not fixed. You have to fix according to the length of the column. You wash the column with the 50 ml of 6 molar ammonia. This is not hard and fast rule. You can even wash or you equilibrate with the eluate what you are using, or even with the mobile phase what you are using. Right? Usually salts can be used, and you can wash the column with 2 molar HCl. So 3 to 4 times or 5 times you wash it, you equilibrate it, so that the column will be appropriately set. There will not be any crack in the column. There will be uniform setting. Then you add a sample. Before that, you can put a small piece of Wattman filter paper, and then you can add the sample. Minimal liquid is recommended, say 0.5 ml, 0.6 ml, or 0.75 ml of sample can be added. You can move up to 1 ml. So gently you add the sample. Then you add enough mobile phase or to the column. Give some time. So the time duration is totally dependent upon the height of the column. If you have selected 20 centimeter, that is the height of the total height of the column, then you provide, say for example, half an hour to 45 minutes. If the column length is 50 centimeter, then you extend the time to 45 minutes or 1 hour. So if you give enough time, then appropriately the sample will get exchanged with the stationary phase material, so that very effectively you can separate or purify. Once the mobile phase tenure is over, and then you can open the stopper, you can remove all the mobile phase, then you add appropriate diluent to when you open the stopper, what happens, suppose if it is a cation exchanger, only cations will get exchanged. So anions and neutrally charged molecules will get eluted, will pass through as such when you open the stopper. So only cations will be present in the column. So once this job is over, now you close the stopper, you add eluent and then open the stopper. Now the eluent should be a strong cation. So now the stuck up sample cation with this stationary phase, that will be disconnected with the eluent strong cation. Now you can remove or separate all the cations which is your interest. So if the molecule of interest is cation, then you have to use a very strong cation element. If molecule of interest is anion, then you have to use a very strong anion. So two things you have to remember in ion exchange. You have to use mobile phase, and finally you have to use a very strong element. But this is not the case in the case of gel filtration. It is not mandatory that you have to use eluent. If it demands, you can use, or otherwise mobile phase itself is sufficient for gel filtration. Whereas in ion exchange, compulsorily you have to use a very strong eluent, because you have exchanged it, and the exchanged sample molecules are still connected with the stationary phase. So in order to remove the purified or separated cations or anions, you have to use appropriate strong cations or strong anions as eluents. So please remember, mobile phase and eluents, both entities are very much important in ion exchange chromatography. So what are the applications? You can purify, you can separate small metal ions. If there is any metal ion contaminants, lead contaminant, mercury contaminant, any contaminant is there in the sample, use ion exchange chromatography and easily you can remove. You won't remove any large molecular weight. As I said earlier, weight is not the influencing factor, only the charge. So molecular weight doesn't bother us when you use this particular technique. So only thing is your molecule should carry some charge. That's all. If it is neutral, try to use some biochemical reaction, try to use some chemical reaction to impart some charge. Neutral molecules cannot be separated. So the main mandatory requirement is only charged species can be separated using this chromatography. Separation occurs because of charge, not because of size or not because of weight. So that really doesn't bother us. So if your protein or polysaccharides, large molecular weight protein, large molecular size polysaccharides you want to separate, if they carry either a plus charge or negative charge, you can use ion exchange chromatography. So not only low molecular weight metals, even you can purify large molecular weight macromolecules. So for desalting, yes, you can use this particular technique. So removal of divalent cations, removal of anions, removal of charged organic pollutants, charged inorganic pollutants. All these things can be done very effectively with the help of ion exchange chromatography. So hope the lecture is useful. Thank you very much.